Homework 8 is due by 1 o'clock on Friday. Then we've got spring break next week, and then on Wednesday after spring break is when homework 9 is due. And then Friday of that same week is when you have to have your first submission for the pipe sizing. That's phase 2 of the project, is where you're using WaterCAD and trying to figure out the optimal size and location of the pipes. And what you're submitting, remember, is 2 maps. One map that shows how your network performs under the design flow, meaning the peak flow rates, and then another map that shows what the pressures look like under the static condition, which is 0 flow rate. Because what we're aiming for is for you to have the smallest possible pipes that manages to have as close to 240 kilopascals under the design condition and no more than 850 kilopascals under the static condition. So all you upload for phase 2 is just those 2 PDF maps. Any announcement questions before we start today's discussion on critical and specific energy? If not, you'll remember that last time we talked about specific energy and alternate depths. And I showed you this graph of specific energy versus depth. And remember, the minimum point that has the lowest specific energy corresponds to the critical depth. And so let's take this same rectangular channel that we were talking about in class on Monday, where we were trying to put 10 cubic meters per second through a channel that has a width of 4 meters. So rectangular channel, there's some water in there. The bottom width is 4 meters. And the flow rate Q is 10 cubic meters per second. And it's the slope of the channel that determines what the depth is. So there could be a really steep slope where there's a fast-moving water velocity, and most of the energy exists in the form of kinetic energy. Or it could be a shallow slope where the water has to be pretty deep, and most of the specific energy exists as the depth because there's very low velocity. Now, specific energy is measuring how much energy is there above the bottom of the channel. And it's the depth plus the velocity head. And you'll remember that sometimes rather than calculating the specific velocity at a location, it's just easier for us to use the flow rate squared divided by the area squared as a surrogate for the velocity squared. So the velocity head term here could be defined by the flow rate Q. So let's go through the process of determining how much specific energy there is for a known depth, and then also finding out what's the alternate depth. What's the other depth that has the same amount of specific energy? All right, so the first part, what is the specific energy when the depth is 0.5 meters? Well, we're going to calculate that with this formula for E. E, the specific energy, is the depth plus Q squared divided by 2GA squared. All right, so that is, the specific energy is 0.5 meters plus the flow rate squared, so 10 cubic meters per second squared, divided by 2G. And now for the area, this is a channel that's 4 meters wide and has a depth of 0.5. So I'll just put those dimensions in here. 4 meters in width multiplied by 0.5 meters in depth. And all of that quantity is squared. Okay, so if you've got your calculator handy, will you calculate what is the specific energy for the depth of 0.5? So we've got 102 times 9.81, 4.5. I just did the calculations here on my calculator. I got 1.7742 ... meaning that there's more and more digits that continue meters. So this is how much specific energy there is. Anybody get that same value, 1.77 meters? Okay. So you'll remember when we were in closed conduit flow, we talked about energy sometimes with units of length, right? We talked about how much head there is, like the pressure head. We measured the amount of energy in units of length. Here, this is a measurement of energy with a unit of length. And some of the energy is the depth, but in this case, most of the energy exists as kinetic energy. So this is down in the supercritical range. If this is the specific energy diagram, our given depth of 0.5 meters is less than what we can clearly see is the critical depth of about 0.86. So at this point, I hope you remember and are able to classify the flow regime based on the depth. So when y equals 0.5 meters, that's less than the critical depth of 0.86 meters. So it is supercritical. So this 0.5 meter depth, that's the supercritical root of the alternate depth, which is going to be a cubic equation. Now the next part of this question is asking, solve the specific energy equation to find the alternate depth for 0.5 meters. Okay, so solve the specific energy equation. So what we know is that the energy is 1.7742, and so 1.7742 meters of energy is equal to y plus q squared. I'm just going to write 100. That's q squared since the q is 10. Divided by 2 times g, so 9.81, times the area, which is 4y, and that is squared. Okay, so 1.7742 is equal to y plus 100 divided by 2.981 times 4y squared. So how are we going to solve for y? Think back into your algebra mindset. How are we going to solve for y? Well, first of all, let's simplify this term over on the right-hand side and just get, like in numeric terms, what is it there? So it's 1.7742 is equal to y plus 0.3186 divided by y squared. So, like if you calculate what is the number down here in the denominator, so it's 100 divided by 2 times 9.81 times 4 squared, so 16. So 0.3186 is in the numerator, and in the denominator is that y squared. Okay, so is everybody with me up to this point? How do we solve for y? Okay. I'm going to suggest what we ought to do first is multiply each term by y squared. So what that's going to lead to is 1.7742 y squared is equal to y cubed plus 0.3186. Okay, so this is the equation that we want to find out what are the roots for y. And I think most of you use those Casio calculators, and you can find the root of a cubic equation. I can do it on my HP. We want to know what are the 3 roots of that cubic equation. So let me bring this up on the screen, and therefore the calculations will be visible in the video for anybody who might be joining remotely. Here we are. So we're at this point. Y cubed minus 1.774 y squared plus 0.3186 is equal to 0. So we want to know there's going to be 3 roots that satisfies that equation. Let me pause for a second and give you a moment to try and calculate what are the 3 roots of that equation. I've never used Wolfram Alpha before, but I saw somebody was doing that. So let's see here. Could we just type in the equation and it'll solve it for you? Do you have to rearrange it, or you can 1.7742 y squared equals y cubed plus 0.3186. Okay. And will it graph that for us and tell us what the roots are? How did you graph it?
Oh, I actually did set it up, sorry.
What do you mean?
0.
Oh, okay. So you had it as y cubed minus 1.774 y squared plus 0.3186 is equal to 0. And it finds the solutions for us. All right. So it says negative 0.38. Let me zoom in on this. Another tool in the tool belt. Wolfram Alpha. 0.3842, which isn't a particularly useful root because we know that water isn't going to flow at a negative depth. So, I mean, that may numerically solve the equation, but we can throw out that root. But we need to put all the roots here. So the roots are negative 0.38. Okay, the root that we already knew, the depth of 0.5. Okay, so 0.50 meters. And then the other root, 1.658. Let's call that 1.66 meters. Here is our subcritical alternate depth, 1.66 meters. Did anybody else get that same depth solving for the roots with the Casio? All right. So the question was asking, solve for the specific energy equation to find the alternate depth for 0.5 meters. Okay, so 0.5 meters is here on the specific energy diagram. What is the other depth, that other crossing point that had the same amount of specific energy? 1.66 meters. So water could flow through a channel and have the same amount of specific energy whether it's at a depth of half a meter, and if it's at half a meter, that's supercritical flow. This 1.66 meter depth would be subcritical flow. And we could put in fact, just because it may be useful to illustrate, let's calculate E for that known depth. So E is the depth y, so 1.66 meters plus q squared, which is 100, divided by 2g, and then the area is 4 by 1.66. 4 by 1.66, and we're squaring that. All right, so let's find out how much specific energy there is, just to double check that truly that depth gives us the same amount of specific energy as when the depth was 0.5. Okay, so 1.66 is the depth, 100, 814, 1.66. So the specific, the kinetic energy component of it here is only 0.1156 meters, and combined with the depth, it's 1.775 meters is the energy. So yeah, that's the same amount of specific energy, 1.775, 1.774, just a round off difference because of me writing the depth here as 1.66 when really it was 1.65812. Now, water goes from supercritical to subcritical in a hydraulic jump, which we're going to go into the lab after spring break and actually take a look at a hydraulic jump. There are other cases, though, where water will toggle between supercritical and subcritical flow. So it's important for us to be able to calculate what's the alternate depth of any particular flow condition. Any questions on the calculations that we've just gone through on how to find the specific energy for a known depth, or how to find the alternate depth once you know a certain specific energy? Any questions?
Where did you get your YC value of the 0.86?
Oh, that's just from last time we were here, from this graph we put together last time. Yeah, good question. But I'll jump ahead. So if you wanted to calculate the YC, we have this formula that we could use to do it. So this is just-in-time teaching. Since you've asked, I'm going to show you this now rather than waiting to the end of the lecture for it. If you have a rectangular channel, which we do, remember this is a rectangular channel that's 4 meters wide. You can calculate something called flow per unit width. So lowercase q is the flow per unit width. And so using the same example we've just been working on, where we have this rectangular channel where the bottom width is 4 meters, and we had a q of 10 cubic meters per second going through here. The flow per unit width, lowercase q, is big Q divided by B. So 10 cubic meters per second going through a channel that's 4 meters wide. So that is, the flow per unit width is it 2.25 cubic meters per second per meter. Let me just make sure it's 2.25. 10 divided by 4. No, it's 2.5. It'll teach me to do math in my head. 2.5 cubic meters per second per meter. So that's just saying, like, in a 1 meter width, how much flow is going through that 1 meter section. Now, once you know the flow per unit width, then you can use this formula for a rectangular channel to find out what's the critical depth. So the critical depth, y sub c, is the flow rate, flow per unit width squared, divided by g to the 1/3 power. So for this example that we're just working, the flow per unit width is 2.5 meters squared per second. So cubic meters per second per meter has the same units as meters squared per second, because you're just basically dividing cubic meters per second by m. And so it's canceling out one of the meters. So 2.5 meters squared per second squared divided by g, which is 9.81 meters per second squared. So Travis asked, how do you know what is the critical depth? You can use this formula for the critical depth if you've got a rectangular channel. So do that. 2.5 squared divided by G, 9.81, and then take it to the power of 1/3, so to the 33333 power. And it tells us that the critical depth is 0.8605 meters. So that's another way. You know, how I had assumed, you know, I'd written it on the board on the basis of those calculations we did last time, when I basically was setting up this table in Excel. And in Excel, what you could do is you could just change a lot of different depths until you found the one that gave you the lowest specific energy. So what I did here was I used Solver, and I said change the depth until you minimize this specific energy. So you could solve for the critical depth that way by minimizing the specific energy, or rectangular channel, use this equation. Thank you for that question. Are there other questions? All right, critical. Supercritical flow, remember, is associated with fast velocity. Subcritical flow is associated with relatively slower velocity. Supercritical flow is when you have the shallow depth. Subcritical flow is when you have the deep depth. Critical conditions is obviously in the middle between super and sub. It's that flow condition that has the minimum specific energy. And there are some things that we can do with obstructions that are put into a channel that forces critical flow conditions. And what's convenient about that, when we force the water to flow at the critical conditions, is that it makes it easier for us to predict the flow rate. And we'll talk about the full details of that. But it's just, the bottom line is it's important to be able to determine the critical depth and to measure how much energy there is when you're at the critical condition. It's the point that has the minimum specific energy. And if you take the derivative of this specific energy equation with respect to y, then you remember we talked about the Froude number in class on Monday, and how the Froude number being greater than 1 is supercritical conditions. The Froude number is less than 1 is subcritical conditions. Let's refresh our memory for this equation for the Froude number. So FR, Froude number, is the square root of Q squared times B, which is the top width, distance, G, and area cubed. So this is the Froude number. And when Froude number is greater than 1, it's supercritical. Less than 1, it's subcritical. And when it's equal to 1, then that's critical conditions. And so all this slide is doing is just saying, when you've got a Froude number of 1, then you can find out the critical depth. If you substitute it in the flow rate and you know the top width, then the only unknown in this, let's say for a rectangular channel, would be the depth parameter that goes into the cross-sectional area. So at critical conditions, the Froude number is equal to 1. So sometimes you need to calculate what is the critical depth. And you could rearrange that equation, because if it's equal to 1, then you could move the area under critical conditions and the top width to the right-hand side of the equation. So just to get some experience using this formula, let's say that we've got that rectangular channel, and calculate the critical depth not with this simplified method. This simplified method only works if it's rectangular, but this works regardless of what the shape is. Like this formula you could use if it's rectangular, or if it's trapezoidal, or a half circle, or triangular. This way of calculating the critical depth always works. Okay, so if the rectangular channel has a flow rate of 10 cubic meters per second, and then the top width is 4, because regardless of depth, the top width is always 4. Find the critical depth. So what we're saying is the flow rate squared is 10 squared divided by G on the left-hand side, 9.81. On the right-hand side, area critical to the cubed power. So it's going to be 4, which is the width, multiplied by y sub c, which is the depth, to the third power, and then divided by the top width when the conditions are critical, which is just 4. Okay, so we want to solve for y sub c here. Okay, so doing that, we would have 100 divided by 9.81 on the left, so that's 10.1936 and so on the left-hand side. And then on the right-hand side, we've got 4 to the third power divided by 4. So 16 yc cubed. Okay, so we could divide the 10 by 16 and then take the cube root of this side and we get the same 0.8604 depth. Okay, so any questions about this formula? Now, of course, where things get interesting is when you've got a trapezoidal channel. So what if you've got a trapezoidal channel with like a 2-to-1 side slope, 2 horizontal for each 1 vertical? Where we're heading is that you need to be able to determine what would be the critical depth for a trapezoidal channel. And this formula will apply, but you'll have to have the area defined as a function of y, but then b will also be a function of y. This top width, the deeper the water gets, the top width is going to be getting deeper and deeper. So let's go back to that table 10.1 that has the geometric parameters. Where's that one? Here we go. So what you'd need to do if you're calculating the critical depth for a trapezoidal channel is that this top width b is going to be, you can see, b plus 2ty, and the area would be b plus ty times y. So the critical depth would be in multiple locations in that formula. And you just have to use Solver, or you could put it in Excel or some other tool to find for the critical depth. All right, I've already jumped ahead to give you this formula, but let me give you a warning with it. I give you a formula sheet to use on your exams, right? And it can be awfully tempting in an exam if I've asked you to find the critical depth. You've got this formula here that says YC, and you think, oh, okay, I'll just use that formula. But most likely, I'd ask you to find the critical depth for a channel that's not rectangular. And so you couldn't use this equation if it was a trapezoidal channel. It won't give you the right depth if it's a trapezoidal channel. So only use this if you have a rectangular cross-section. All right, we've already found the critical depth, so we don't need to do this example. All right. Slope. Critical slope is the slope that causes critical flow. So Manning's equation is here. And well, let me write it the way that I usually like to see it, which is area to the 5/3. I've probably got that somewhere and I can just paste it down. There we go. I like that form of it a little bit better. It ends up being fewer places that we have to solve for y. Let's do this. Okay. So we've got a trapezoidal concrete channel. The fact that it's concrete defines the n value that goes into Manning's equation. The bottom width is 3 meters. It's got side slopes of 1.5 to 1. So the 1.5 is the horizontal component, and the 1 is the vertical. So that just basically means that T is 1.5. And the flow rate is 186 cubic meters per second. So we know Q. We didn't yet solve for the depth. And we want to know what slope will cause the critical depth. So here, this equation we can use to find the depth, the critical depth, and then once you have the critical depth, you can put it into Manning's equation and solve for S. So it's a two-step process. Step 1, find YC, the critical depth, using this equation of Q squared divided by G is equal to AC cubed divided by TC. Well, top. I think that's B. The top width when conditions are critical. Okay, so find the depth with that. Basically, we've rearranged this equation for what I've written on the whiteboard. And then step 2 is with YC known, substitute into Manning's equation, and solve for S. So solve for what slope would cause the critical depth. And you can see here I've given you the formulas that you need for the top width, the formula that you need for the area, the formula for wetted perimeter, for this intermediate parameter W, and that should, I guess, be a lowercase w. All right, any questions on what we're doing here? All right, I'm going to pause the recording, give you some time to do these calculations. Okay, so the critical depth should be 4.121 meters. We've got a bottom width of 3, 1.5 horizontal for every 1 unit of vertical on the sides. So if we put that into the Froude number equation and set the Froude number equation equal to 1 and then solve for the depth, y, it should be 4.121 meters. Now, you can rearrange Manning's equation to solve for slope. So if we rearrange Manning's equation to solve for slope, then it's going to be S is N times Q divided by area times hydraulic radius to the 2/3 power divided to the power of 2. Or if we use this approach, it would be Q times N times P to the 2/3 divided by area to the 5/3, and then square all of that. Okay, so when we determined that the critical depth is 4.121 meters, then we can find the wetted perimeter, the cross-sectional area, put those things in, hydraulic radius, and the critical slope is 0.0015. So 0.15% is the slope that would cause critical flow through this channel. Okay, so that is critical slope and some additional practice having to do with specific energy. Any questions about these calculations? All right, well, I'll see you on Friday then. Take care, everybody.